Hello, my name is Paul Geyer, and I'm here to chat with you today about exterior mechanical utility distribution systems. This is what I'll be talking about, kind of the chapters in the book: design responsibilities, distribution site location factors, service and loads, and specific piping design factors. By way of introduction, this is a little bit about me and what I've been doing for the last few decades. Got registered in a few different things along the way, but I'm basically a mechanical engineer. The project designer is responsible for accomplishing the following prior to project bidding: define the site conditions for underground water classification, soil corrosiveness, soil pH if less than 5, and potential soil load bearing problems. Determine the general layout and essential characteristics of the system, such as system medium, maximum operating temperature and pressure, location and design of manholes and branch runouts. The interface detail of the system at manhole walls shall be provided by the system supplier. Design special elements of the system as required and calculate the maximum heat loss per lineal foot of the conduit. The project designer shall design on project drawings the exterior steam and condensate piping systems above ground, the manholes, piping within manholes, and piping not in approved conduit systems. The project designer shall establish the system design parameters of the entire underground piping system, such as site classification, general layout, essential characteristics of the system, and specially designed elements of the system. The project designer is responsible for sizing the pipe, establishing the piping elevations, identifying the piping right-of-way, obstructions and utilities, plan and profile within 25 feet of the center line of the right-of-way, and every area within 25 feet of the center line that must be avoided, for example, paved areas and buildings. The project designer is also responsible for the location and sizing of manholes, the design of concrete manholes, and the piping and equipment layout of manholes, including valves, fittings, traps, expansion joints when required, and manhole drains. The construction contractor shall design and provide buried factory prefabricated pre-insulated piping in a conduit or pre-engineered insulated piping system which owner has approved. It is intended that the supplier of an approved system provide the details of design for his system in accordance with the owner's requirements. The pre-approved design will address expansion loops, bends, offsets, concrete pipe anchors outside of manholes, and interface with each manhole and the watershed to above ground piping. When prefabricated steel manholes are indicated, the system supplier is responsible for the structural design of the manhole and the manufacture of the complete manhole, including installation of valves, fittings, and other equipment as specified herein and indicated on the project drawings. The contractor is responsible for the design, fabrication, and installation of the underground piping system within the system design parameters established by the project designer. Fluid distribution site locations should be established according to the following. Location factors, refer to Table 1. Subsurface explorations. When a concrete trench or a buried steam or hot water system is specified, make a thorough investigation of ground and water conditions. Employ a soils engineer familiar with groundwater conditions at the site to establish the classification. In the absence of existing definitive information on soil types and groundwater conditions, make a detailed site classification survey. Upon completion of the survey, classify each exploration point as A, B, C, or D on the basis of the criteria presented in Tables 2 and 3. The worst groundwater condition encountered between adjacent manholes determines the class of the system to be installed between adjacent manholes. Conduct this survey within the guidelines specified. Conduct the survey after the general layout of the system has been determined. Make the survey at a time of year when the highest water table is expected to exist, if possible. If this is not possible, correct water table measurements on the basis of professional judgment to indicate conditions likely to exist at the time of year when the water table is at its highest point. As a minimum, collect information on groundwater conditions, soil types, terrain, and precipitation rates and irrigation practices in the area of the system. Information on terrain and precipitation rates and irrigation practices may be obtained from available records at the installation. Make test explorations such as borings or test pits at least every 100 feet along the line of a proposed system. If changes in stratification are noted, decrease the boring spacing so an accurate horizontal soil profile may be obtained. Table 1 indicates location factors for each distribution system. Table 2 on slide 11 indicates soil classification. Table 3 on slide 12 provides soil classification criteria. Extend all explorations 5 feet below the expected elevation of the concrete trench invert or the depth of the pre-engineered system to determine groundwater conditions. Give particular attention to the following conditions: the possibility that the ground below a backfilled piping system may not be able to absorb runoff that is seeped into it, areas where ponding may occur either along a sloping surface or in low flat areas, and the permeability of the ground below the system. Perform field permeability tests as follows. Space field permeability tests, percolation tests, along the line of a trench at intervals of approximately 100 feet. When available information indicates uniform subsurface conditions, longer intervals may be allowed for larger projects. Dig holes approximately 1 square foot to a depth of 2 feet below the approximate bottom of a trench. Fill each hole with water to the bottom elevation of the planned trench. After the water has completely seeped away, immediately refill each hole with water to the same depth. If it requires 20 minutes or less for the water to drop 2 inches, consider the soil dry. Otherwise, consider it as saturated at times. Use test results as follows. If the soil is saturated, no further tests are required. Class A underground conduit systems for wet soils must be used. If the soil is dry, as defined above, deepen permeability test holes an additional 3 feet to determine if the water table is within 5 feet of the trench bottom. Considerations for soil resistivity are as follows. Take soil resistivity readings along the conduit line in accordance with Table 1. A cathodic protection system is required to protect metallic piping systems and manholes. This applies to all sites where soil resistivity is less than 30,000 ohms per centimeter, where stray current, direct currents can be detected underground, or where underground corrosion due to local soil conditions has been found to be severe. Have an experienced corrosion engineer make the classification based on a field survey of the site carried out in accordance with recognized guidelines for conducting such surveys. Classify the soil at the site as corrosive or non-corrosive on the basis of the following criteria. Corrosive, the soil resistivity is less than 30,000 ohm centimeters, or stray direct currents can be detected underground. Non-corrosive, the soil resistivity is 30,000 ohm centimeters or greater, and no stray direct currents can be detected underground. During the above survey, observe and note the soil stability. Note areas of unstable soil on the site plans depicting the distribution route. As a part of the project designer's survey, have an experienced soils engineer investigate the load-bearing qualities of the soil in which the system will be installed. Identify the location and nature of potential soils problems. Depending on the nature of the problem, the designer may choose to reroute the line, use a combination of concrete shallow trench, direct buried, or above ground low profile systems, or elect to over-excavate and replace with non-expansive fill. Base selection of the conduit system type on the underground water conditions at the project site as defined in tables 1, 2, and 3 for Class A, B, C, or D application corresponding to underground water conditions ranging from severe to mild respectively. Class A, severe, the water table is expected to be frequently above the bottom of the system, or the water table is expected to be occasionally above the bottom of the system, and surface water is expected to accumulate and remain for long periods in the soil surrounding the system. Class B, bad. The water table is expected to be occasionally above the bottom of the system, and surface water is expected to accumulate and remain for short periods or not at all in the soil surrounding the system, or the water table is expected never to be above the bottom of the system, but surface water is expected to accumulate and remain for long periods in the soil surrounding the system. Class C, moderate, the water table is expected to never be above the bottom of the system, but surface water is expected to accumulate and remain for short periods in the soil surrounding the system. Class D, mild, the water table is expected never to be above the bottom of the system, and surface water is not expected to accumulate or remain in the soil surrounding the system. No system may be installed without prior approval of the owner. A system approved for higher classification is acceptable for use in lower classifications. For example, Class A is acceptable for classes B, C, and D, etc. The highest groundwater level evident during the wettest period of the year should be a minimum of 1 foot below the lowest point of water entry into the concrete shallow trench system required for these areas when in an environment of fine-grained impervious soils. The lowest point of entry is defined as the joint between the concrete trench wall and concrete trench bottom. The concrete trench bottom will be continuous with no openings. The above condition will ensure that constructability of the concrete shallow trench is practical and that potential infiltration of water into the shallow trench will be negligible. Open drainage ways, swales, or swampy, boggy areas will preclude use of a concrete shallow trench system because of groundwater level guidance in Table 2. The concrete shallow trench system must be rerouted or regraded to bring the concrete trench out of the unsuitable conditions. Have the geotechnical engineer who performed the detailed site classification survey provide regrading instructions. The designer will ensure that the fill will remain stable and will not be subject to future washouts. If the specific site conditions are such that these alternatives are not viable, consider above ground low profile or a direct buried system of the prefabricated or pre-engineered type in accordance with the owner's requirements for these areas. In swelling soils, if the specific site conditions are such that these alternatives are not viable, consider above ground low profile or a direct buried system of the prefabricated or pre-engineered type in accordance with the owner's criteria for these areas. Design the concrete shallow trench system in materials having high swell potential. Soils having a liquid limit greater than 50 and a plasticity index greater than 25 require testing for consolidation swell to determine the swell characteristics. When the results of the swell test indicate high swell potential, special considerations such as over-excavation, width and depth, and replacement with non-expansive fill, under trench drainage system, or other methods of minimizing differential heave will be provided. The design of special features such as described above will be in accordance with instructions provided by the geotechnical engineer who performed the detailed site classification survey. Design of joint spacing and joint details to accommodate movements will also be provided when required. With regard to settlement of trenches, generally, settlement of concrete trenches will not be a problem since the unit load of the shallow trench system will be similar to the existing unit overburden load. Backfill adjacent to the concrete trench must be thoroughly compacted to prevent settlement, which would create ponding. Positive slopes away from the concrete trench are desirable. Special care of backfill and compaction is required where the system crosses existing streets to preclude settlement and cracking of the roadway adjacent to the trench from repeated traffic loads. Use concrete trench subdrain systems as required. When subsurface conditions are of differing soil types, fine-grained and coarse-grained as an example, and those differing soil conditions will cause blocked drainage either horizontally or vertically adjacent to the concrete trench, provide subdrains to ensure drainage to prevent ponding or entrapment of water adjacent to the shallow trench system. Base the design of the subdrain system on the instructions provided by the geotechnical engineer who performed the detailed site classification survey and classified each exploration point. Soils of low permeability and high moisture content shall not require underdrains when the shallow trench system is designed to accommodate all anticipated inflow with systems or equipment, such as direct connections to storm sewers or the use of dual sump pumps. Connect drainage system sump pump discharge pipes to storm sewer system where feasible. If not feasible, provide discharge to splash blocks on grade. When discharging to grade, install the pump discharge line without a check valve to allow complete drainage of the discharge pipe to prevent freezing. Do not use under-trench drainage to alter groundwater level to meet requirements of Table 2. With regard to the use of reinforced thermosetting resin plastic pipe, RTRP, RTRP pipe is normally supplied when used for condensate systems. This pipe is suitable for service pressures up to 150 psig and temperatures up to 200 degrees Fahrenheit. Above 200 degrees Fahrenheit, the pressure rating drops off rapidly. At 250 degrees, the pressure rating is 125 psig and drops to 45 psig at 270 degrees Fahrenheit. These ratings are for hot water. Live steam cannot be tolerated, although RTRP pipe may be used for vented gravity condensate piping as well as for pumped condensate piping. RTRP pipe is acceptable at Class B sites. It is recommended for Class A sites as permitted by the owner due to its low cost and long service life. Procure and install RTRP condensate piping in accordance with the owner's requirements. Take special care in the design of steam drip connections to protect the RTRP piping from live steam from failed traps. Insulate condensate piping only when a life cycle cost analysis indicates a payback in energy savings or where needed for personnel protection, such as in manholes. Determine from the services such as steam, high temperature water, hot water, chilled water, compressed air, fuel gas, and others required for each load center or building, the load demands for each service, and the capacity of a source or central plant for each service. Refer to the appropriate master plan and consider system routing and size to accommodate future construction. From the total allowable pressure drop and ultimate length of a line, determine the pressure drop per 100 feet. Note the maximum flow between each load center and size the different pipeline sections accordingly. From a field survey, note all obstacles for each route. Refer to the master plan and consider system routing to accommodate future construction. Select a circuit which is economical, easy to operate, balance and control, and is suitable for a particular project terrain. Note that types easiest to balance and control are those where pressure and temperature differences are fairly constant between equipment supply and return branches. Run distribution piping through buildings above ground or underground and below piers. Select the route considered technically and economically best justified through buildings. Make full use of building piers, underpiling spaces, basements, crawl spaces, and attics, including connecting corridors between buildings, existing tunnels, and concrete trenches. However, high-pressure fuel, gas, steam, and high-temperature water piping inside buildings should be routed to comply with federal and local fire and life safety codes. Gas piping shall comply with ANSI B31.8 gas transmission and distribution piping systems and NFPA 54 National Fuel Gas Code. Steam, condensate, and compressed air lines shall comply with ANSI B31.1 power piping. With regard to exterior steam distribution, use owner's requirements for all steam distribution piping exposed to the weather or on building exteriors, above ground piping supports, piers, pedestals, poles, and for all steam piping on piers and under piers, in tunnels, and in manholes. Use owner's requirements for piping in trenches. Use owner's requirements for buried steam piping. With regard to above ground overhead piping, locate piping as low as 1 foot or as high as 22 feet above the ground surface. A 16-foot clearance is required for automobile and truck traffic and a 22-foot clearance for railroad cars. For buried piping routes, the following criteria apply. First of all, compressed air and gas piping. Compressed air and gas piping generally require no insulation, but they should be shop coated, wrapped, tested, and handled in accordance with owner's requirements. Provide for testing of coverings by electrical flow detectors, spark testing. Protect all buried piping and conduits by laying them under a minimum cover of 24 inches. However, protect buried piping under railroads, roads, streets, or highways, or due to changes in ground contours against possible external damage due to the superimposed car or truck traffic. Lay pipes below the frost line. Casings may be needed where there is no frost. When piping must be laid where it will be subjected to hazards such as earthquakes, washouts, floods, unstable soils, landslides, dredging of water bottoms, and other categorically similar conditions, protect it by increasing pipe wall thickness, constructing intermediate supports or anchors, erosion prevention, covering pipes with concrete, adding seismic restraints for above-ground piping or other reasonable protection. With regard to manholes, select manhole locations in accordance with the following. Details of piping and design of manholes are the responsibility of the project designer. Design manholes to provide adequate space for maintenance, proper venting, and quick egress. Manholes are required where vertical offsets in steam piping are required to conform to grading requirements. Manholes accommodate the required steam main drip traps and any block valves needed. Manholes are usually provided at all major branch line connections and at drip traps on compressed air lines. With regard to tunnels, construct tunnels for underground routes with a walkway minimum height of 76 inches and clear width of 36 inches, with piping stacked vertically on one side and enlarged zones for crossovers and takeoffs. Label all pipes and conduit. Provide enough room to reach all flanged bolts to operate tools and to operate or to replace any component. Run a drainage trench along one wall to a point of disposal such as a storm sewer or a sump pit with an automatic drainage pump driven by an electric motor or steam jet. Install all electrical systems in rigid metal conduit. Identify and separate by voltage class. Tunnels shall be well lighted and ventilated. Use moisture-resistant electrical fixtures. Tunnels may be built of reinforced concrete, brick, or other suitable structural materials and shall be membrane waterproofed. Except in congested and vulnerable areas, choose above-ground routes for heat distribution systems. Otherwise, adapt site conditions to comparative advantages of going above or underground as stated below. Slide 36 provides these recommendations. The project designer is responsible for determining the location of expansion bends, loops and joints, anchors, takeoffs, isolation valves, and drip points. The project designer is also responsible for locating all manholes, takeoffs, isolation valves, and drip points. The system designer determines the initial location of anchors, expansion bends, loops, and joints. The system supplier determines final location and design of these features to fit actual field conditions. Plan and position piping layouts as follows. Determine what lines between the same point should be parallel to each other, such as supply and return, or be separated, such as steam and chilled water. The minimum clearance between pipe conduits in the same trench shall be 6 inches. Determine locations of expansion bends or loops, anchors, takeoffs, and drip points. In non-pre-engineered, prefabricated heat distribution systems, the project designer is responsible for determining location of expansion bends, loops and joints, and anchors, takeoffs, isolation valves, and drip points. In pre-engineered, prefabricated heat distribution systems, the project designer is responsible for locating all manholes, takeoffs, isolation valves, and drip points. Initial location of anchors, expansion bends, loops, and joints shall be by the system designer. The system designer determines the initial location of anchors, expansion bends, loops, and joints. The system supplier determines final location and design of these features to fit actual field conditions. Lay out piping on a scaled contour map of the site and on a profile drawing along the route, locating all obstructions and interferences such as streams, roads, railroads, buried tunnels, concrete trenches, drainage piping, sewers, water piping, electrical conduits, and other service piping within 25 feet of the center line of the right-of-way, and identify areas within 25 feet of the center line that must be avoided. If sufficient right-of-way to accommodate pipe expansion cannot be identified and expansion joints are required, they must be specified and located with installation details noted on the drawings. Provide a log of soil conditions along the piping right-of-way, which gives as a minimum soil type, soil resistivity, and pH, bearing strength, and unstable conditions, and indicate corrective work required. Provide details at building entries on the project drawings to show pipe elevation, floor elevation, building wall construction, and existing equipment. Underground, use only approved and certified conduit systems for steam, condensate, and high temperature water, and procure and install in accordance with the requirements of the owner. Concrete shallow trench systems may be used only if the soil characteristics set forth by the owner are met. With regard to insulation, evaluate insulation for all piping systems with the potential for significant thermal losses. These include steam, condensate, high temperature water, medium temperature water, low temperature water, and chilled water piping. Anchor or guy exterior distribution systems to withstand the wind velocity specified for design of structures. Specific piping design factors, fluid characteristics. If steam is the media, refer to Keenan and Key's thermodynamic properties of steam. For condensate, for the economics of returning condensate, use the ASHRAE Handbook Fundamentals and the ASHRAE HVAC Systems and Applications Handbook. For high temperature water, medium temperature water, and low temperature hot water, use ASHRAE Handbook HVAC Systems and Applications and the ASHRAE Handbook Fundamentals. For compressed air, refer to the owner's requirements. For natural gas, refer to NFPA 54. With regard to distribution system piping, equivalent lengths of piping to the straight lengths of pipe along a pipeline route, add equivalent lengths for valves and fittings as indicated in Table 4. Size distribution piping as follows. Minimum pipe size, use minimum of 2-inch pipe, which requires extra strong piping for direct buried piping with threaded end connections sized for piping in shallow trench system with all joints welded. Smaller pipe sizes and threaded joints are allowed in valve manholes. For steam piping, the project designer shall specify the design temperatures and pressures. The approved systems are suitable for temperatures of up to 450 degrees Fahrenheit. If higher temperature systems are required, review the manufacturer's approved brochures to determine the exceptions to the brochures to be made in the project specification relative to pipe material, pipe expansion, and valve classification. Design considerations are Table 4 indicates representative equivalent length in pipe diameter to ratio length to diameter for various valves and fittings. Steam flow charts for pressures of 30 psig, 50 psig, 150 and 150 and 100 and 150 psig. Refer to figures 1 through 4. These charts show weight rate, pressure drop, and velocities of saturated steam in Schedule 40 steel pipe. By selecting all pipe sizes on an optimum pressure drop, the total pressure drop of a pipeline may be estimated from an equivalent length, irrespective of pipe size. The charts are based on the rational flow formula, Darcy. For higher pressures, refer to the Piping Handbook by Crocker and King. The simplified rational flow formula, the Darcy equation, is used for compressible fluids for all pressures as indicated on slide 47. For velocities, refer to Table 6. Table 1 indicates the chart for weight, flow rate, and velocity of steam, 30 psig. Table 2 is the chart for weight, flow rate, and velocity of steam for 50 psig systems. Table 3 indicates the chart for weight, flow rate, and velocity of steam for 100 psig systems. Table 4 indicates the chart for weight, flow rate, and velocity of steam for 150 psig systems. Figure 5 indicates the value of C1 flow factor used in equation 1. Table 5 on slide 54 indicates values for C2, the flow factor used in equation 1. Table 6 on slide 55 indicates reasonable velocities for flow of steam in pipes. With regard to steam distribution pressures, steam pressure is governed by the highest pressure needed by the equipment served at the most remote location, as well as by an economic analysis of the feasible systems, including pressure considerations. The advantages of a low pressure system under 15 psig are low distribution loss, lower losses and less trouble from leakage traps and venting, simplified pressure reduction at buildings, standard steel fittings, and low maintenance. The advantages of high pressure distribution over 50 psig are smaller pipe sizes, availability of steam for purposes other than for heating, and more flexibility in velocities and pressure. With regard to selection of valve types, install double-ported pilot-operated valves for large capacities, especially for inlet pressures above 125 psig. Double-ported valves will not shut off completely on no load demand, therefore single-seated valves must be used for such services. Do not install reducing valves on the basis of pipe sizes because oversized valves do not give satisfactory service. Select valves to operate generally fully open with ratings and reduction ratios as recommended by the manufacturer. Install a strainer and condensate drain ahead of the pressure reducing valve. Because the volume of steam increases rapidly as the pressure is reduced, a reducing valve with increased outlet or expanding nozzle is required when the reduction ratio is more than 15:1. Provide cutout valves to isolate the pressure reducing valve to permit maintenance. Where the resulting superheated steam temperature is objectionable to the process on the low pressure side, or the temperature use limit of the equipment has been exceeded, a de-superheater must be used to lower the steam temperature to that for saturation. Provide a manual bypass for emergency operation when the pressure reducing valve is out of service. Provide a pressure gauge on the low pressure side. Where steam requirements are relatively large, above approximately 3,000 pounds per hour, and subject to seasonal variation, install two reducing valves in parallel, sized to pass 70% and 30% of maximum flow. During mild spring and fall weather, set the large valve at a slightly reduced pressure so that it will remain closed as long as the smaller valve can supply the demand. During the remainder of the heating season, reverse the valve settings to keep the smaller one closed except when the larger one is unable to supply the demand. Provide one or more relief or safety valves on the low pressure side of each reducing valve in case the piping and/or equipment on the low pressure side do not meet the requirements of the full initial pressure. The combined discharge capacity of the relief valves shall be such that the pressure rating of the lower pressure piping and equipment will not be exceeded. For special conditions, refer to ASME B31.1 and ASHRAE Handbook Systems and Applications. With regard to takeoffs from mains to buildings must be at the top of mains and located at fixed points of the mains at or near anchor points. When a branch is short, valves at each takeoff are unnecessary. Takeoffs shall have valves when the branch is of considerable length or where several buildings are served. A 45-degree takeoff is preferred. 90-degree takeoffs are acceptable. Branch line slope of 1/2 inch should be used for lines less than 10 feet in length and should be 1/2 inch per 10 feet on branch lines longer than 10 feet. Condensate returns are preferred if owning and operating costs of such a system are less than that of using and treating raw water for makeup. Factors favoring condensate return are high area concentration of steam usage, restriction on condensate disposal, high raw water treatment costs, water treatment space unavailable, high cost of raw water, and high cost of fuel for feed water heating. Design considerations are as follows. For the return piping, size condensate trap piping to conform with 30 to 150 psig steam piping in accordance with tables 7 and 8 and interpolate those for other pressures. With regard to discharge piping, size discharge piping from condensate and heating pumps in accordance with pump capacities, which may be between 1 to 3 times the capacity of the steam system branch which they serve, depending on whether continuously or intermittently operated. Table 7 indicates return pipe capacities for 30 psig steam systems. Table 8 indicates return pipe capacities for 150 psig steam systems. Size common pump discharge mains to serve the sum of their capacities. Use the Hydraulic Institute Pipe Friction Manual for steel pump discharge pipe sizing of new clean steel pipe, 6 feet per second maximum velocity, and a correction factor of 1.85 to provide for increased pressure drops when the pipe becomes dirty and rough with age. Friction plus static heads shall not exceed the pump characteristics of standard pump and receiver units. With regard to high temperature water piping is as follows. Sizing of pipe. Use pipe friction charts in ASHRAE 1985 or later Handbook of Fundamentals. These charts are based on the rational flow formula using clean pipe. A reasonable average velocity is approximately 5 feet per second. The minimum allowable velocity is 2 feet per second. For methods of venting high points of distribution lines, refer to the owner's criteria. Piping must have drainage means at low points. For chilled water piping, use the standards of the Hydraulic Institute Pipe Friction Manual for sizing new clean pipe unless water is renewed annually, in which case a correction factor of 1.41 for pressure drop is also to be used. For recommended velocities, refer to the owner's criteria. For condenser water piping, use the standards of the Hydraulic Institute Pipe Friction Manual for pipe sizing, multiplying the pressure drop by a factor of 1.85 to correct for the increase of pipe roughness with age. For recommended velocities, refer to the owner's criteria. No correction factor is required for RTRP pipe. With regard to natural gas piping, apply the owner's criteria for sizing pipe inside buildings. Use Figure 6 for low volume flow rates and Figure 7 for high volume flow rates in sizing distribution piping. Using these figures will simplify design of piping by indicating required diameter, maximum rate of flow, permissible pressure drop, initial pressure, or final pressure when the rest of these values are known. These charts are based on the Weymouth formula for rate of flow in cubic feet of gas per hour. The chart is based upon the following conditions: gas at 60 degrees Fahrenheit and specific gravity of 0.6, where air is 1.0. Exterior distribution piping usually stops 5 feet outside of buildings. With regard to compressed air, for criteria on distribution piping, refer to the owner's criteria. Figure 6 indicates low volume flow rate natural gas chart. Volume in cubic feet per hour on the horizontal axis and pressure drop in inches of water per 100 feet on the vertical axis for pipe design factors. Figure 7 indicates piping design factors for use on high volume flow rate natural gas systems, 1,000 to 1 million cubic feet per hour. Piping specification codes are as follows. For steam supply and condensate return, piping shall conform to ASME B31.1 except for underground, prefabricated, or pre-engineered type systems, in which case the entire system shall conform to the owner's requirements. If a separate pump condensate return system is used, it shall conform to the owner's requirements. For condensate provided as a part of an underground, prefabricated, pre-engineered system, include owner-approved plastic condensate piping in the specification as a contractor's option for sites classified B, C, or D. Plastic piping is optional but encouraged for sites classified A. The owner's representative shall give specific approval for plastic condensate piping in Class A systems. Take particular care that the failure of high-pressure steam drip traps shall not discharge high temperatures and pressures into the plastic condensate pipe. With regard to high temperature water, medium temperature water, and low temperature hot water systems, piping specifications and codes are as follows, except for underground, prefabricated, or pre-engineered types, in which case the entire system shall conform to the owner's requirements. Piping, high temperature water metallic piping, 450 degrees Fahrenheit, and medium temperature water metallic piping shall conform to ASME B31.1. Welded joints are preferred. Threaded joints are not permitted. Hold flanged joints to a minimum and use ferrous alloy gaskets in such joints. Avoid the use of copper and brass pipe. All valves shall have cast steel bodies with stainless steel trim, no bronze trim. All valves shall be capable of being repacked under operational pressures. Use gate valves only as shut-off or isolation valves. For natural gas and compressed air systems, piping shall conform to ASME B31.1 and B31.8, including guidance for abandoning existing gas lines. Note that ASME B31.8 requires that abandoned gas lines be physically disconnected from gas sources and purged prior to sealing. Shut-off valves are not an acceptable means of disconnect. Cathodic protection systems on lines to be abandoned should be evaluated for modifications required to ensure continuity of the systems after abandoned lines are disconnected or removed. Provide excess flow earthquake shut-off valves in gas supply piping outside of each building served in earthquake zones 3 and 4. In addition, provide flexible connections. Gas piping and appurtenances from point of connection with existing system to a point approximately 5 feet from the building shall conform to the owner's requirements. With regard to chilled and condenser water, use Schedule 40 steel pipe in 10-inch size and smaller, and use half-inch wall thickness steel pipe for 12-inch size and larger. RTRP pipe and PVC pipe are also acceptable. RTRP pipe and PVC pipe are available in 2 through 12-inch pipe sizes. With regard to thermal expansion of steel and copper pipe, pipe expands with temperature increases such as between installation and operating temperatures, as indicated in Table 9. Make provisions for the control of expansion in any piping system where thermal expansion is a factor. Wherever possible, provide for expansion of pipes by changes in direction of pipe runs. With regard to branch lines, where practicable, design branch line piping to provide for expansion inside buildings. Expansion control of branch lines should be designed so as to have no effect on main. Bends are to be factory fabricated except for RTRP pipe. Loops may be furnished in sections to facilitate delivery and handling. Anchors, a reasonable distance between anchors for expansion loops is 200 feet for 125 psi steam systems. Expansion is usually kept at about 6 inches between anchors. With regard to cold springing, it may be used in installations, but no design stress relief is allowed for it. For credit permitted in thrust and moments, refer to ANSI B31.1. Install expansion joints only where space restrictions prevent the use of other means. When necessary to use, expansion joints shall be in an accessible location and shall be one of the following types: mechanical slip joints, an externally guided joint designed for repacking under operating pressures. Hold maximum traverse of piping in expansion joints under 8 inches. For bellows type joints, use these joints on steel pipe for thermal expansion with stainless steel bellows guided and installed according to the manufacturer's instructions. Make bellows or corrugations for absorbing vibrations or mechanical movements at ambient temperatures of copper or other materials suitable for the job conditions. A maximum travel of 4 inches is allowed for this type. RTRP expansion joints may be poly tetrafluoroethylene bellows type. Install flexible ball joints according to the manufacturer's instructions. Refer to ASME B31.1 for expansion and flexibility criteria and allowable stresses and reactions. Table 9 indicates pipe expansion in inches per 100 feet of length for the temperatures indicated. For methods of analyzing stresses in piping systems, use piping handbooks and publications of pipe and pipe fitting manufacturers. These manufacturers also supply calculation forms and charts. Keep calculated pipe stresses under those allowed by ANSI B 31.1. Insulate piping systems as required by the owner. Insulation thicknesses shall conform to owner requirements. However, in locations where extreme annual temperatures occur, the project designer should evaluate different thicknesses of insulation. Make final selection based on an economic analysis. Design insulation jackets in waterfront or other locations subject to flooding to drain. They shall not be watertight. Drainage provisions must conform to the requirements discussed below. With regard to pitch, the surrounding terrain and piping application both affect the pitch of piping as indicated below. Horizontal piping, pitch horizontal steam piping down at a minimum of 2.5 inches per 100 feet of length in the direction of steam flow. For underground piping, pitch horizontal piping down towards drain points, unless otherwise noted, a minimum of 2.5 inches in 100 feet. Where the ground surface slopes in the opposite direction to steam piping, step up underground piping in vertical risers at drip points in manholes and pitch them down to the next drip point. Use this method also for all very long horizontal runs above or below ground to keep piping within a reasonable range of elevations with reference to the ground surface. With regard to counterflow conditions, where counterflow of condensate within the steam pipe may occur in a portion of a pipeline because the stepped construction cannot be built or because of steam flow reversal in a loop system, pitch that portion up in the direction of steam flow a minimum of 6 inches per 100 feet and increase pipe diameter by 1 standard pipe size. Pitch compressed air and gas piping as for steam piping. Pitch pumped water pipes, condensate, high temperature water, medium temperature water, low temperature water, chilled water, or condenser water, up or down in direction of flow at a minimum of 2.5 inches per 100 feet of length. Place drain valves at all low points and vents at high points. Provide drips and vents as follows. With regard to drip legs, provide drip legs to collect condensate from steam piping and compressed air piping for removal by automatic moisture traps or by manual drain valves for compressed air piping when practicable. Locate drip legs at low points at the bottom of all risers and at intervals of approximately 200 to 300 feet for horizontally pitched pipe where a trap is accessible, and not over 500 feet for buried underground pipe systems. On gas piping, drip legs are not usually required where dry gas is provided. Where there is moisture in the gas, provide drip legs and sediment traps in accordance with NFPA 54. Automatic traps are not utilized. With regard to water piping, vent piping, especially high temperature water piping at distribution piping high points. For fuel gas piping, provide capped dirt traps at vertical risers upstream of gas burning devices. For condensate systems, furnish a complete system of drip traps and piping to drain all steam piping of condensate from drip legs. Ensure drip piping to traps is the same weight and material as the drained piping. Preferably run a condensate line from a trap directly to a gravity condensate return main or to a nearby flash tank. Refer to the ASHRAE Systems and Applications Handbook for flash tank details and specific trap applications. However, a trap may be discharged through a check valve into the pumped condensate line if pressure in the trap discharge line exceeds the back pressure in the pumped condensate line during standby time of an intermittently operated pump. If the pumped condensate line is RTRP pipe, install a condensate cooling device similar to that shown in Figure 8 to limit the temperature of the condensate entering the line to less than 250 degrees Fahrenheit. Select traps using a safety load factor no greater than 2. The condensate load should be indicated on design drawings and may be determined for above ground lines by using Table 10. The condensate load for underground distribution lines is determined from maximum heat loss as indicated by the design. With the tight safety load factor for sizing traps, an alternative method of expelling gases during warm-up is required. To this end, all strainers should have blowdown valves, which will also be used for controlled warm-up. Pitch discharge piping down a minimum of 3 inches per 100 feet to the collection tank. This applies where a condensate pump set or reliance upon a gravity return is used. An exception to this rule of thumb exists when there is sufficient pressure in a steam line to overcome its friction and static head, whether the line is level or pitched up. Trap discharge line shall not be RT-RP pipe, nor shall the trap discharge connect to an RT-RP pipe by direct connection. Install pipe through a condensate cooling device as depicted in Figure 8. This system provides a cooling tank and diffuser plus a temperature relief valve to limit the temperature of condensate returned to a pumped RT-RP condensate line to less than 250 degrees Fahrenheit. Table 10 indicates condensate loads from above ground heat distribution piping in pounds per hour per 100 linear feet. If it is not justifiable to return drips to a condensate system, they may be drained as waste to a sewer. If the temperature exceeds sewer limitations, condensate must be cooled in a sump or by other means. Disposal of condensate from steam systems along the waterfront or under piers warrants special consideration to be determined on a case-by-case basis. Ensure that pipe anchors comply with the following criteria. Locate anchors for non-pre-engineered prefabricated systems at takeoffs from mains and other necessary points to contain pipeline expansion. If possible, locate anchors in buildings, piers, tunnels, and manholes with suitable access. Design and locate anchors in accordance with ASME B31.1. Design anchors to withstand expansion reactions. With expansion joints, consider the additional end reactions due to internal fluid pressure and add end reactions due to spring rate of the joint. Anchors for elevated above ground systems shall consist of wire rope guys running from embedded concrete deadmen to pipe saddles welded to the pipe and secured to the vertical supports. Guy in both directions. Guys may be located on the diagonal to serve also as sway bracing. In underground concrete tunnels, the ends of structural steel shapes anchoring a pipe may be embedded in the tunnel walls or floors. Ensure that pipe supports conform to ASME B31.1. For above ground systems at low elevations, defined as lower than 5 feet above grade or the working surface, use and space concrete pedestals, steel frames, or treated wood frames as required depending on pipe sizes. At higher elevations above ground, support pipelines on wood, steel pipe, H-section steel, reinforced concrete, pre-stressed concrete poles with cross arms, or steel frameworks fitted with rollers and insulation saddles. Refer to Figure 9. Details of design will vary depending on site conditions. Figure 8 indicates a protective arrangement for RTRP pipe when long spans are necessary. Cable suspension or catenary systems may be used. Used approved types of manufacturers' standard design supports for underground conduits. In trenches, suspend pipes either from the walls or the tops of the walls. Do not support piping from either the floor of the trench or from the removable top. The pipe hanger design must provide for adequate system expansion and contraction. All non-insulated ferrous parts of the piping support system or equipment will be hot dipped galvanized or primed with red oxide primer and painted with epoxy paint. For concrete trenches, the concrete shallow trench will consist of poured concrete sides and floor with removable tops. Portions of the floor may be omitted at locations outlined previously under coarse-grained soils with water table 2 feet or more below the lowest point of water entry. Ensure the depth of the concrete trench is sufficient to provide adequate protection to the piping system, and slope the floor of the trench to provide adequate internal drainage, but in all cases not less than 6 inches from the bottom surface of the suspended pipe insulation to the floor of the trench. Ensure there is a minimum of 3 inches between the surface of the pipe insulation and the adjoining trench walls, and a minimum of 4 inches between surfaces of adjacent pipe insulation. Figure 9 indicates a typical above-ground pipe support. With regard to the drainage of trenches, base the design on sound engineering principles which provide for drainage under all anticipated conditions. Consider the annual rainfall, water table, and other topographic conditions in the basis for the design. For those instances where natural drainage cannot be provided, stormwater drainage system at least 2 feet below trench bottom at all times. Provide a dual sump pump capability with failure annunciator. The tops of the concrete trenches will be removable by use of a portable lifting device such as a forklift or backhoe, and can also be used for sidewalks if practical. Earth must not cover the tops. Covers will be close tolerance fit with a maximum gap tolerance buildup of 0.12 inches from all causes. Design the concrete shallow trench heat distribution system and show on the contract drawings. Use figures 10 through 21 as appropriate. Provide the following information on the contract drawings for the concrete shallow trench system as applicable. Dimension on all runs of pipe, elevations of the pipe along the system's path, sizes of the pipe, location of all valves, location and details of all expansion loops, Z and L bends, location of pipe anchors, how changes in pipe direction are made, thickness of the insulation on the pipe, concrete trench details, final elevation of concrete trench, profile of trench showing all existing utilities, manhole dimensions, manhole cover details, how manhole is drained and vented where required, sump pump piping details, sump pump capacity, condensate pump capacity and details, include specific requirements for modifications to existing, steam drip trap locations and capacity, steam pressure reducing valve capacity and details, and other pertinent information and details required to clearly show the intent of the shallow trench heat distribution system. Also indicate any obstructions in the path of the distribution system that the contractor may have to work around. Extend valve manholes at least 9 to 12 inches above finished grade to prevent seasonal runoff from entering, except where trench will be a pedestrian walk, in which case the valve cover will be flush with the trench covers. Where required, provide inspection ports at appropriate locations to enable the user to observe drains or expansion at loops or locations requiring frequently, say monthly, observation. At all road and railroad type crossings, provide required slab thickness for railroad crossings and H20 loading for street crossings. Review railroad track removal replacement with respective authority and coordinate all activities. Road and rail crossing where maintenance of traffic is critical may be accomplished by jacking using an acceptable conduit tunnel. In addition to or in combination with a poured-in-place concrete shallow trench system, a precast or prefabricated shallow trench system consisting of precast concrete covers, concrete trench, or supports may be specified. If the designer selects this option, he must include special details and specification requirements of the precast system and the transition between the poured-in-place and precast systems. Provide sump pumps in manholes. Units should discharge by buried piping to nearest storm sewer if possible. Where not economical to discharge to storm sewer, pumps are to discharge above grade to splash blocks. Plan discharge locations carefully so water will not be placed over tunnel tops, sidewalks, etc. Use sump pumps capable of passing 3/8 inch solid spherical minimum. Adjust float switches so the pumps start sequentially, reducing electrical line surge. Coordinate power requirements with electrical designer and provide telltale light above ground to indicate that power is available to sump pumps. If portions of manholes are installed below the water table, waterproof that portion below the water table. Pipe entry for buried pre-engineered systems piping shall be in accordance with Figure 22. Figure 10 on slide 97 indicates a concrete shallow trench heat distribution system defined as detail 1. Figure 11 on slide 28 is another concrete shallow trench heat distribution system identified as detail 2. Figure 12 on slide 99 is another concrete shallow trench heat distribution detail I characterized as detail 3. Figure 13 on slide 100 provides additional concrete shallow trench heat distribution system details identified as detail 4. Figure 14 on slide 101 provides additional concrete shallow trench heat distribution details identified as detail 5. Figure 15 on slide 102 provides additional concrete shallow trench heat distribution system details identified as detail 6. Figure 16 on slide 103 provides additional concrete shallow trench heat distribution system details identified as detail 7. Figure 17 on slide 104 provides additional concrete shallow trench heat distribution system details identified as detail 8. Figure 18 on slide 105 provides sump details for a concrete shallow trench heat distribution system identified as detail 9. Figure 19 on 106 provides typical valve manhole details for concrete shallow trench heat distribution systems identified as detail 10. Figure 20 indicates typical valve manhole covers in walkways and typical lifting devices for valve manhole covers in walkways. Figure 20 Figure 21 on slide 108 indicates a typical standard valve manhole cover and typical lifting ring. Figure 21 is identified as detail 12. And figure 22 on slide 109 indicates steam pipe manhole entry detail for concrete shallow trench heat distribution systems identified as detail 13. And that brings us to the end of this brief discussion of exterior mechanical utilities distribution systems. I hope that this has been somewhat helpful to you and that will give you some tools to address projects of this type that come across your desk in the future. And so again, thank you very much for letting me chat with you and have a nice rest of the day.